Welcome to the fourth day of FDP on Advanced Technology for Efficiency and Sustainability. Good evening, respected dignities, resource person and faculty members. Now, I would like to introduce today's resource person, Dr. K. Venkateswarlu. It is my pleasure to introduce our estimate resource person, Dr. K. Venkateswarlu. Kavati Venkateswarlu is currently working as an associate professor, Mechanical Engineering, School of Engineering and the Built Environment, JEDS Campus University of Namibia. He received his BTech in Mechanical Engineering and MTech in Thermal Engineering for JNTU College of Engineering, Hyderabad, and PhD in Mechanical Engineering IC Engines from JNTU Kakinada in 2016. He did his postdoctoral research at RAC Research and Innovation Center, American University of Ras Al Khaimah, UAE. He has 4 years of industrial experience and 23 years of teaching and research experience in the field of thermal fluids and energy. So his research interests include low carbon technologies for IC engines, fuel injection strategies for supersonic combustion engines, phase change materials for thermal energy storage, and energy dissipation in soil samples, and nanofluids in heat transfer and solar energy application. Dr. K. Venkateswarlu has published 30 research papers in national and international journals of repute. He has guided 14 MTech theses and guiding 1 master and 1 doctoral thesis. He has authored 2 textbooks, Engineering Thermodynamics, Fundamentals and Advanced Topics and Alternative Fuels and Advanced Vehicle Technologies. He has also authored 3 book chapters, Low Energy and Low Carbon Building for a Sustainable Future, Clean Energy for Sustainable Electric Power Generation and Combined Heat and Power Generation for Hydrogen and Application. A very warm welcome from our side, sir. Thank you for coming in this program of our college.
Hello, sir.
Yeah. Good evening, Governor all. Good evening. Am I audible?
Yes, sir. Your voice is audible, sir.
Okay. Thank you very much for your introduction. So, unmute is okay. Right. Okay. Okay. Thank you. Right. The video రావట్లేదా? Okay. Right. Right. Thank you. Yeah, good evening, one and all. So I'm here to talk on hydrogen energy in aviation, considering the two important aspects related to the sustainability as well as carbon neutrality. So these two aspects play an important role in mitigating the climate change and its mitigation effects. So basically, sustainability of energy sources. Sustainable energy means it should be capable of meeting the present demand without compromising the future demand. So, for example, if you use solar energy for power generation, electricity generation, its use will not impact the future generations' usage. Similarly, the carbon neutrality is important for achieving the what is called as net zero emissions by 2050 or 2060. So these are my topics of presentation. So I'm going to talk on aviation demand and energy intensity and carbon intensity of energy for aviation and the contribution of global aviation to the climate change and the characteristic features required for aviation fuels, and then pathways to achieve net zero emissions from aviation, hydrogen in aviation. So here I'm going to compare the properties of hydrogen fuel with other aviation fuels and other factors as well. Then hydrogen fuel powered aircraft, hydrogen fuel cell powered aircraft, and hydrogen fuel cell powered scramjet engine, and hydrogen production and storage methods, and finally challenges associated with widespread adoption of hydrogen in aviation. So basically, aviation demand increases due to several reasons, maybe due to the increased population, increased income, and increased business activities, maybe globalization and other factors. So the global aviation demand increases year by year. So this is the graph showing the aviation demand from 1990 to 2025, and then the projected aviation demand from 2025 to 2050. So we can see here the aviation demand was nearly 1 billion kilometer equivalent, 1 billion ton kilometer equivalent in 2019. It's almost 80% demand coming from the passenger or commercial aircraft, and then 20% from cargo or freight. And if you consider the projected aviation demand in three scenarios, one is business as usual and industry and ambitious projections from 2025 to 2050. We can see that the business as usual case, the projected growth rate of aviation is nearly 4% every year, whereas in the industry scenario, it is around 3%. But whereas in the ambitious case, it is 1% growth every year from 2025 to 2050. So this is the aviation demand, both current as well as and projected demands. So here it is 1 trillion ton kilometer equivalent, or it is 11 nearly 11.1 what is called as passenger kilometer equivalent. So this is the worldwide passenger aircraft fuel consumptions. So in the 1985, the fuel consumption was 8 liters per passenger per 100 kilometers, whereas it was 5 liters in 2005. Now it is around 3 liters per passenger for 100 kilometers. Because of the increased what is fuel efficiency or aircraft technology enhancements and other factors, the fuel consumption reduced from 8 liters in 1985 to 3 liters at present. So basically, energy intensity is the amount of energy required to produce certain output. So that means if you reduce the energy intensity of energy, any activity, so we can enhance energy efficiency. So that means energy efficiency is dependent on energy intensity of any activity. Similarly, the carbon intensity of energy is the amount of carbon dioxide produced by uh, the amount of carbon dioxide emitted to generate 1 kilowatt-hour of energy. So obviously, the fossil fuel-based power generation results in more amount of carbon intensity. So these are important parameters So basically, aviation doesn't mean aircraft alone because it consists of several activities. Maybe airports. In airports, there is energy usage for various activities for running air conditioners, other devices, and the vehicles, ground vehicles use ground transport vehicles use fuel, maybe diesel or other things. So that means aviation consists of aircraft and other things which are taking place in the airports. Yeah, this is the energy intensity variation from 2000 to 2025. We can see that energy intensity decreases up to 2019 maybe because of COVID, maybe travel advisories and what is called as travel restrictions and border restrictions. There was a decline and there was increase in the energy intensity during the COVID period. And again, there is a decline. So that means energy intensity decreases gradually in aircraft. So this is the fuel consumption trend of different aircraft. So we can see here for 150 passengers with 1 hour flight can consume, let us say Boeing 747 consumes more than 3,000 liters of kerosene, whereas Airbus 380 consumes nearly, it is also more than 3,000. So because these two aircraft are powered by 4 turbofan engines, so they consume more than 3,000 liters of kerosene for 1 hour with 150 passengers. Yeah, this is the pollution trend emitted by air transport. And this is also for 1 hour flight with 150 passengers. It's a two engine jet, which consumed around 2,700 liters of kerosene, which emitted 8,500 kg of CO2. So this is the carbon dioxide emission of typical flight with two engine jet. And you can see here, the fuel consumption trend and the projected cases. So we can see here the fuel consumption can be reduced if there is no aircraft technology enhancements or improved air traffic management. We can see that nearly 27% of what is called as reduction in the fuel consumption by 2050, out of which the 22% coming from this aircraft technology improvements, whereas nearly 5% coming from the improved air traffic management. So that is by 2050, it is possible to reduce fuel consumption by 27% with enhancement in aircraft technology as well as international what is called as air traffic management systems. Similarly, we can see that CO2 emissions also can be reduced by 27% with these contributions by aircraft technology enhancements as well as improved air traffic management. But however, if the sustainable aviation fuels are considered as fuels, there is a further reduction of nearly 55% in the CO2 emissions. Yeah, basically the aviation contributes towards climate change. It emits CO2 as well as non-CO2 emissions, including what is called as sulfates, nitrogen oxides, and other things, water vapor or whatever it is. So these will contribute towards global warming because they trap the heat energy which is reaching the Earth's surface. So here there is a factor known as radiative forcing, which is the difference in energy that is between the incoming solar radiation as well as outgoing terrestrial radiation. So that means this radiative forcing is used to measure the what is called as imbalance in the atmosphere, energy imbalance in the atmosphere. So that means radiative forcing is high means the imbalance is also high. So we can see here the radiative forcing in watt per meter square in 1992 as well as in 2050. Yeah, we can see here it is nearly the total radiative forcing is nearly 0.04 watt per meter square in 1992, but whereas it is 0.2 in 2050. So that means the radiative forcing is going to be very high in 2050 because of this CO2 as well as non-CO2 emissions emitted by aviation industry. Let us see the characteristic features required for aviation fuels. Basically, the aviation fuels require high specific energy as well as high energy density, so that they can power long haul aircrafts. In addition to that, they should have some good atomization, evaporation characteristics, and they should be pollution free, and they should have high specific heat capacity and low viscosity, high lubricity like that. And also the fuel should be stable both thermally as well as chemically, and it should be available widely with reasonable price, and it should have a good handling characteristic as well. So aviation fuels are basically categorized into two groups. One is gasoline-based aviation fuels, which were used to power the first generation aircraft, which are basically reciprocating piston engines, so just like internal combustion engines. So they use the gasoline-based aviation fuels. And then nowadays we are using, of course, kerosene-based aviation fuels, which are called as aviation turbine fuels, because the current aircraft are powered by gas turbine engines. So they use kerosene-based aviation fuels. So basically, kerosene has several advantages as an aviation fuel. Basically, it is cheaply available, and its stability is also good, and its flashpoint range is also in the range of minus 35 to minus 35 to 60, so that it is stable at atmospheric conditions, and its freezing point is also around minus 45 degrees centigrade, so that it will not freeze during the high altitude conditions where the temperature may be minus 20 degrees, where the flight travels at high altitude, where the temperature, atmospheric temperature is minus 20 degrees centigrade. And kerosene freezing temperature is nearly minus 45 degrees centigrade, so it will not freeze at high altitude where the aircraft flies. So these are some of the salient features of kerosene as an aviation fuel. But however, there are certain drawbacks. The kerosene can power long-range aircraft because of its high energy density. But however, the yield percent of kerosene is quite low. It is only 10% from the crude oil. And another important drawback is it's a hydrocarbon-based fuel. It will result in greenhouse gas emissions. So it will lead towards global warming. So that's the reason there is a need to evolve alternative fuels or energy sources for aircraft, maybe in the or aviation also. So aviation totally putting together, it contributes towards global CO2 emissions. So there are 3%. Aviation contributes nearly 3% of the global CO2 emissions. But putting together other non-CO2 emissions also, it is 3.5% of the global emissions. And again, both CO2 as well as NOx emissions are expected to rise by 21% and 16% by 2040 related to 2015. And so there is a need to develop fuel efficient aircraft as well as there is a need to reduce the noise as well. Of course, over the period of time, there is a gradual improvement in the noise as well as fuel efficiency. And another important factor is the use of plastics to reduce the overall weight of the airplane. It also add to the pollution because of the plastics. So these are the pathways to achieve net zero emissions by 2050 or 2060 as mandated by Intergovernmental Panel on Climate Change, IPCC. So these are the different alternatives: enhancements in operations and infrastructure, and increased aircraft efficiency, optimized air traffic management, utilization of sustainable aviation fuels, and implementation of carbon offsets, maybe carbon capture and storage, and carbon capture and utilization. So these are the various alternative pathways to achieve net zero emissions from aviation. So here, if you consider the case of operational improvement, basically aerodynamic design will reduce in weight as well as drag resistance, so that the fuel consumption can be reduced. So the fuel consumption reduction will obviously lead towards reduction in the emissions. And the aircraft cabin equipment with lightweight materials, and then electric or assisted taxiing. So turning off the main engine during the taxiing, landing as well as takeoff times, turning off the main engine and running the aircraft electrically or other assisted other alternative power sources, so that the fuel consumption can be reduced here, which is electric or assisted taxiing. and thinner paints as well as other measures can be taken to improve the operational improvement. Then the infrastructure improvement also plays a vital role in enhancement of efficiency and then fuel consumption mainly. So improvement in airports and decision making, effective decision making and surface congestion management also lead towards improvements in infrastructure. So increased aircraft efficiency is another important parameter. So there are several alternatives in this case. Effective design of the aircraft and weight reduction and operations management and use of alternative fuels, which will so that the fuel consumption can be reduced, and improving the infrastructure, aircraft and traffic, reducing the traffic distance and other things. So sustainable aviation fuels basically can reduce CO2 emissions by nearly 80%. And also there is a possibility that they can be produced from variety of feedstocks, including waste fats, oils, and greases, municipal waste, and other things. So they can also be produced from synthetically, so that there is a possibility of carbon capture from the air. So these are the advantages of sustainable aviation fuels. And also early SAFs used the alkanes, but with the advancement in the technology, aromatics as well as cycloalkanes are also a part of that aviation fuels. So these alkanes, aromatics basically improve the sealant performance so that the leakage can be prevented. So these sustainable aviation fuels are called sustainable because their feedstocks will not compete with the food crops or other water resources or other things. Okay, that is the reason they are called as sustainable aviation fuels. So this is the pathway for decarbonization of aviation. So in the first generation aircraft use gasoline. Okay, gasoline. They are the gasoline powered aircraft, and then current aircraft use kerosene. And before this liquid hydrogen is a reality, of course, the battery and electric aircraft and liquid hydrogen powered aircraft is a reality. There are some transition fuels like synthetic fuels, biofuels. So that means the transition between kerosene and liquid hydrogen. These are the transition fuels, synthetic as well as synthetic jet fuel, which is a combination of which is produced from carbon dioxide and hydrogen. Okay, CO2 plus H2, that is synthetic kerosene. So this is the pathway for decarbonization of aviation. And existing aviation fuels or energy sources, if you consider there are basically four main alternative fuels as well as energy sources. So we can see that sustainable aviation fuel is one of the options. Then electric aircraft and hybrid solutions and hydrogen. So so we can see here if you use sustainable aviation fuels, no, the methane can we can see that the ratio of thrust, okay, the thrust can be enhanced by nearly 45% and 22% by using this methane when compared to that of jet A1 and kerosene, whereas novel sustainable aviation fuel will result in 17% thrust when compared to that of jet A1 and almost equal ratio of thrust with kerosene. So this increase in ratio of thrust will obviously result in increase in ratio of range available. So we can see here increase in this so 45% and 22% ratio of thrust will lead towards increased ratio of range. We can see here 20% and 11% more range available with CH4 when compared to jet A1 as well as kerosene. And similarly, this novel jet fuel will result in 10% more ratio of range and nearly equal ratio of range when compared to kerosene. So because of this usage of sustainable aviation fuels. So, but however, there is one drawback with this sustainable aviation fuels. Mainly, it's the alkanes which are a part of a part of this sustainable aviation fuels, they don't comply with ASTM standards that are required for aviation fuels, mainly in terms of freezing point as well as flash points. This is one of the drawbacks. And then the production cost at present is also high, and also the issues related to its integration into the industry because of their no, current aviation industry is also one of the drawbacks. And then and its production also depends on feedstocks availability, cost effectiveness, and route also. Route selection is also one of the important difficulties. Okay, so based on this, its production is something less. So if you see the SAF production, global sustainable aviation fuel production, up to 2015, it was less than 2 million ton liters. So from 2007 to 2015, the SAF production was even less than 2 million ton liters. But however, from 2016 onwards, with increase in advanced technologies and cost reduction and the policy changes, there is a surge in global SAF production. And electric aircraft is another alternative, but however, these electric aircraft it's only suitable for low range or short haul operations only, because as of 2019, lithium ion battery storage capacity was less around 250 to 300 watt hour per kg. But however, the projected maximum specific energy is nearly to 500. So that means this electric aircraft can be suitable for short haul operations, maybe local regional aircraft. So this is we can divide the commercial aviation aircraft into three categories. One is regional narrow body and wide body airlines. So we can see here this regional aircraft. The specific energy requirement is nearly 600, but whereas for this narrow body, it is more than 800. And wide body airliner requires specific energy of nearly 1300 watt hour per kg. So that means these are three different types of commercial aircraft: regional, narrow body, and wide body. So that means for powering wide body airliner, the battery capacity is insufficient. It's only suitable for maybe regional aircraft. So short haul aircraft, the battery electric aircraft may be suitable if it is powered by battery. Then hybrid solution is another option. So it can address the issue of short haul, maybe powering the long range operations. So hybrid electric propulsion can be a viable solution to overcome the drawbacks of fully electric aircrafts. But however, the drawback with this is the components such as electric motors and batteries. The integration and the thermal management is a big challenge for these electric motors as well as batteries. So, and designing the waste heat generation system is also very complex. And again, if you add something of thermal management components, it adds to the weight of the aircraft. So it is another limitation. So that is the reason hybrid aircraft is also not fully reality. Okay, so then hydrogen is another alternative fuel. So it basically hydrogen is widely available mainly, and its important features include it has wide flammability limits, so that it can be combusted in lean combustion systems. So which will be useful for reducing NOx emissions, because NOx emission formation tendency is very high when the combustion temperatures are high. So because of this wide flammability limits, hydrogen can be used in lean combustion engines, so that NOx tendency can be reduced. And again, hydrogen has high flame speed, so it also contributes towards reduction in the so residence time can be reduced. So the residence time of the fuel air in the combustion chamber can be reduced, so that the peak temperatures can be reduced, which will also reduce NOx emissions further. But the only drawback is hydrogen may escape easily from inside the fuel systems. So, but however, the adoption of hydrogen combustion as well as fuel cell engines is more important. So, to achieve the better possible outcome from either hydrogen combustion or hydrogen fuel cells, its adoption is so important to achieve its full capacity. Then hydrogen production pathways. So actually, there are three different production sources to produce hydrogen. One is fossil fuel based and renewable energy renewable sources, and nuclear energy based one. So hydrogen is basically produced from fossil fuel based sources with steam, methane reforming, gasification, and pyrolysis are the three important methods to produce hydrogen from fossil fuel based sources. And it can be produced from renewable sources as well and nuclear energy also. Electrolysis is one of the most predominantly used technique for producing hydrogen from renewable sources and even nuclear energy also. So nuclear energy based methods include thermal as well as electrical and a combination of these hybrid also. So hybrid thermochemical and electrical methods also. So these are the hydrogen production pathways. Fossil fuels, mainly coal, oil, natural gas. So steam methane reforming is the most widely used technique for producing hydrogen from fossil fuels. And from renewable sources, so mainly electrolysis and nuclear based. There are two methods, mainly the thermal and electrolytic, as well as a combination of these two hybrid also. So, so these are the hydrogen production from renewable sources: solar, wind, geothermal, biomass. So variety of feedstocks can be utilized for this producing hydrogen from renewable sources. And from nuclear energy, the two important methods, thermal, electrical, and hybrid also, hybrid thermochemical, which combines both thermal as well as thermochemical as well as electrical. And high temperature electrolysis is another technique. So that means nuclear energy can be utilized to the electricity from nuclear reactor is used to electrolyze water in the reactor, okay, in the electrolysis process. So these are the two methods, and another one is hybrid thermochemical method. So the global H2 production, if you consider the resources, so natural gas is on the top, which constitutes 47% of the global hydrogen production. And then next to that, 27% from coal and 22%, 27% from coal and 22% from oil. And only 4% is produced from electrolysis process. So that means the most of the hydrogen is produced from natural gas, which is it constitutes 47%. Then come oil as well as coal. But however, hydrogen production from electrolysis is quite low. That is only 4%, less than 5%. So, but however, electrolytic hydrogen production at current at around 2021, it was 0.7 gigawatts, but it is expected by 2050 that nearly 5 terawatt capacity by 2050 to achieve what is called as 1.5 degree pre-industrial temperatures. So we can see here the comparison of hydrogen production and the cost as well as efficiency. If you see that efficiency and cost here, both steam methane reforming SMR and as well as plasmosis are the two methods with highest efficiency, nearly 80% each. So the hydrogen production efficiency is more in case of steam methane reforming as well as plasmolysis. So that is around 80%. The cost also, the cost of the SMR is low, but however, this cost of the plasmolysis is something high. But however, this SMR obviously emits greenhouse gases. So that is the reason it cannot be no viable option at all to produce hydrogen However, it is currently produced predominantly with this SMR method. And if you compare the global warming potential and the stratospheric ozone depletion potential of various hydrogen production methods, you can see here the conventional hydrogen production results in more amount of what is called as GWP. And see, we can see here the conventional hydrogen production, it has highest value of GWP as well as ozone depletion potential, stratospheric ozone depletion potential SOD. So that means the conventional production of hydrogen has highest value of GWP as well as SOP. And in the renewable sources, we can see that the PV is on the top. But here, the biological production of hydrogen, the GWP as well as SOD are quite low. So that is dark fermentation and photo fermentation are the methods used to produce biologically hydrogen. So that means in the in the renewable case, PV is on the top and dark fermentation, both dark fermentation as well as photo fermentation are the methods which will result in low GWP as well as SOD. The hydrogen production, the different colors, we can see that gray hydrogen. So based on the process and source and carbon output, we can categorize hydrogen production into three categories. One is gray hydrogen, blue hydrogen, and green hydrogen. So gray hydrogen is produced by SMR and autothermal reforming. And here the natural gas is the main resource. And its carbon output is around 10 kg. But blue hydrogen is it is something carbon capture and storage method. It's the source is CO2 rich stream. So that means CO2 can be captured from the air, and its carbon output is less than 5 kg. And another method is green hydrogen. So it is by using a process known as electrolysis. So the source is water. It doesn't emit any carbon related emissions. So that is that these are three different categories of hydrogen based on the source and process technology and carbon outputs. So these are the hydrogen storage methods. Basically, there are two types of hydrogen storage, physical based and material based. And the physical based storage, compressed gas storage, compressed storage as well as cryocompressed and liquid hydrogen. Compressed gas is basically the hydrogen is stored around in between 350 to 700 bar pressures, high pressures. And this liquid hydrogen is that is storing the hydrogen at around minus 253 degrees centigrade. So this is the boiling point of hydrogen is 20 Kelvin or minus 253 degrees centigrade. So liquid hydrogen is stored at around minus 253 degrees centigrade. So that is cryogenic storage. And another method is a combination of this liquid and gaseous phases. That is cryocompressed hydrogen storage method. So that means it is high pressure and low temperature. So the gas is basically compressed, then it is cooled. So it's a combination of these two things. So liquid as well as gas phases. So cryocompressed storage is advantageous when compared to these two methods because it combines these two techniques. And material based techniques, there are two methods, chemical sorption as well as physical sorption. So here in the chemical sorption, the hydrogen is basically reacted with some kind of metal hydrides. But whereas in the physical sorption, it is like with low molecular interactions. So it is just absorbed on the metals or whatever it is, without any chemical reactions. But here in the chemical sorption, there is a chemical reaction so that hydrogen can be reacted with metal hydrides or whatever it is. So cryocompressed storage offers high storage density when compared to other methods. So based on the storage pressure, the tank mass increases. So here we can see that up to 14 bar, the tank capacity in case of titanium tank, it is constant. But however, with increase in storage pressure, the tank mass increases, both in case of titanium as well as carbon tanks. That is for storage purposes. So that means we can store up to 14 kg, and the tank mass remains constant, but however it increases with increase in the storage pressure. So now, if you consider the hydrogen as a gas turbine fuel, basically its energy density, its gravimetric energy density is nearly 3 times higher than kerosene, but however its volumetric energy density is quite low, so which necessitates large volume, large storage tanks. Though its mass density, volumetric energy density is, that means density per unit mass is more, but density per unit volume is very less. So volumetric energy density is very less when compared to that kerosene. So it requires large storage capacities. So, so we can see here the slide with kerosene tanks. So we can see that the kerosene tanks can be, storage tanks can be on the wings in case of kerosene based aviation fuels are used. Whereas if hydrogen is used as a fuel, you can see that it is the main body. So the fuselage is, the tank should be located in the fuselage so that it reduces what is called as the passenger. It will reduce the capacity of the passengers to whereas in the kerosene it can be stored on the wings, but whereas here the hydrogen should be stored on the main body so that it will reduce the passenger capacity of the aircraft. So this is this is hydrogen fuel cell hydrogen fuel cell powered aircraft. So hydrogen storage, and this is fuel cell, and this is electric motor. So here hydrogen generates electricity in the fuel cell. Hydrogen is used in the fuel cell to generate electricity. So this electricity powers the electric motor. So electric motor powers the aircraft. And if you compare the hydrogen with other aviation fuels based on fuel properties, energy use, carbon intensity, and global warming potential and cost, we can see that the hydrogen actually its density is quite low, and again its energy density, though gravimetric energy density is 3 times higher than kerosene, its energy density, volumetric energy density is quite low, so it requires large storage tank capacity. So because its density is also low, and if you see here, compare the volumetric energy density and mass energy density, we can see here the liquid hydrogen, though its mass energy density is high, its volumetric energy density is low when compared to that kerosene. So kerosene has highest volumetric energy density, but whereas liquid hydrogen, its volumetric energy density is low, though it has high mass energy density. And also, if you compare the energy specific fuel consumption of kerosene and hydrogen, we can see that hydrogen hydrogen requires nearly 3% less fuel energy when compared to the kerosene. So here we can see that it is 28, 29. So that means 3% less fuel energy than kerosene. Hydrogen requires 3% less fuel energy than kerosene for a specific cost. And if we compare the energy use of hydrogen with other aviation fuels, we can see that up to design point, hydrogen requires less energy when compared to the kerosene. But however, between 1000 and 4000 nmi, where most of the nautical miles, where most of the wide body airlines operate, its hydrogen requires nearly 10 to 30% more fuel energy. So that means within the range of 10 to 1000 to 4000, hydrogen requires 10 to 30% more fuel energy when compared to that of aviation fuels. But however, at design point, up to design point, it requires less energy when compared to that of kerosene or aviation fuels. And we can see here the engine performance data. So that turbine inlet, the temperature is low in case of hydrogen. It is nearly 60 Kelvin low in case of hydrogen-based aircraft. So that means it will help reduce the burden on the gas turbine blades. So because the gas turbine blades are exposed to this high temperature, but whereas in case of hydrogen-powered aircraft, it is 60 Kelvin less. And if you compare the carbon intensity of fuels, we can see that green liquid hydrogen powered fuel cell powered aircraft will reduce carbon intensity by nearly 85% when compared to that of jet A. And when compared to that e-kerosene, this green liquid hydrogen fuel cell powered aircraft will result in 35% carbon intensity than e-kerosene and 88% low carbon intensity when compared to that of jet A fuels. So this is the comparison of carbon intensity of various fuels. And if you compare the global warming potential of various fuels, we can see that ethanol, liquid ammonia, they have highest global warming potential, kg of CO2 equivalent per ton or kilometer. But here we can see that if the liquid ammonia is produced from renewable sources, its global warming potential is something reduced. So we can see that if it is liquid ammonia is produced from other renewable sources, we can see that it is reduced. But however, liquid hydrogen, liquid hydrogen is produced from renewable sources like wind, hydrothermal, or geothermal. Its global warming potential is quite low. And this is a fuel price comparison. So we can see that e-kerosene, the fuel price projection from 2030 to 2050, we can see that it is this jet A fuel price remains almost constant on 2030 to 2050. But however, this e-kerosene will be the expensive, and we can see that the fuel prices of anyhow from 2030 to 2050, the fuel price of green hydrogen as well as green liquid hydrogen will come down. We can see that in both United States as well as European Union, both the prices will be reduced in case of green hydrogen as well as green liquid hydrogen. So this is the liquid hydrogen demand global as well as European Union. So the demand increases from 2040 to 2050, the demand of liquid hydrogen increases. That is more in case of turbofan engines. We can see here, when compared to the turboprop engines, the turbofan engines, the liquid hydrogen demand will be very high when compared to that of turboprop engines. So now I'll discuss something hydrogen in ramjet engines. So basically, ramjet engine is a modified version of ramjet engine. So a ramjet is a jet engine, air-breathing jet engine, but however, it doesn't require a compressor. So the ram effect will compress the incoming air, so that it will avoid it eliminates the use of compressor and hence the turbine. So the ramjet is also an air-breathing jet engine, but it is used to power missiles and space vehicles. So if you see that, if you compare the various hypersonic propulsion systems, you can see that the specific impulse. So if you compare the specific impulse of various jet engines and rocket engines, we can see that at high Mach numbers, the turbojet engine specific impulse is quite low. So that means the turbojet engine specific impulse drastically reduces with increase in Mach number. So similarly, ramjet also, ramjet can be efficient up to 6 Mach number. So it can operate between 3 to 6 Mach number. But turbojet is effective up to 3 Mach number only. But however, it operates less than 1 Mach number. So ramjet can be effective or efficient in between 3 to 6, but its performance decreases with increase in Mach number. which is not suitable for hypersonic propulsion. So, but scramjet, it is more efficient at high Mach numbers. So we can see that scramjet can be effective at high Mach numbers, and then rocket, its thrust is quite low. It is of course constant. So that means if you compare the specific impulse of jet engines and rocket engines, we can see that scramjet is more efficient at high Mach numbers. So which is a modified version of ramjet engine. So in case of ramjet, combustion is supersonic. So that means air travels at supersonic speeds, whereas in ramjet engine, the air travels at air is decelerated to subsonic velocities for combustion, whereas in the ramjet, the air travels at supersonic velocities. But however, so this both ramjet as well as ramjet can be utilized in powering the missiles and space vehicles. So Russia used the scramjet engine to power its missiles during the Ukraine war in 2023. So, but however, there are certain challenges in supersonic combustion ramjet or scramjet engines, because its fuel resistance time is quite low, which is some milliseconds at high Mach numbers. Because in the supersonic combustion, the mixture should the air should travel at high velocities in order to reduce what is called as total pressure loss and total heat generation. Okay, so in order to reduce total pressure loss and heat generation, the air should travel at high velocities. But however, at high Mach number, the fuel air residence time is quite low, which is some milliseconds. So obviously, at high Mach numbers, it will the fuel air residence time is quite low. So that is one of the challenges. But however, the ignition delay of the kerosene is longer, so it requires longer. What is called as it requires extensive atomization before igniting. So that is the reason kerosene may not be a viable option in scramjet engines because of its longer ignition delay. But hydrogen, if you compare the hydrogen with kerosene, its flame speed is high. So that's the reason hydrogen can be a viable option in scramjet engines. So in order to overcome the drawbacks of the scramjet engine, like to enhance fuel air mixing, so there are certain techniques, fuel transport and fuel air mixing process. One is intrusive method and non-intrusive method. So the fuel injected from obstruction like certain ramp is called as an intrusive method, whereas wall injection and cavity-based injection is they come under the category of non-intrusive methods. Okay, so non-intrusive methods, the fuel can be injected, maybe a direct injection from the combustor walls or from cavities. These cavities are wall mounted, basically maybe top wall or bottom wall mounted cavities. So, and combining these two techniques, so that is non-intrusive method. So non-intrusive methods include wall injection as well as cavity-based injection, whereas fuel injection from obstruction is called as strut injection or ramp injection. So if you compare the cavity and strut injection cases, we can see that basically strut, in case of strut, the fuel is injected into the core of the flow, but whereas in case of cavity injection, the drawback is fuel will not reach the core flow. That is one of the drawbacks. But however, this strut can be utilized for uniform combustion, whereas cavity can be preferable for effective mixing. So this is a typical cavity. So we can see this is a bottom mounted wall cavity here. So the cavity, the purpose of cavity is to enhance the specific area so that it can increase the turbulence, and of course which will be helpful for effective fuel air mixing. So this is a bottom wall mounted cavity. The cavity can also be mounted on the top wall like this here somewhere. So this is a basically bottom wall mounted cavity. So the strut injection is both the strut as well as cavity injection are widely researched fuel injection strategies in case of scram jet engines. So both strut as well as cavities. So again, in the strut, there are several configurations are researched. So this is a typical strut that is used in the DLR combustor. So we can see that this is the leading edge of the strut. So that means the strut can be placed as an obstruction in the combustor, so that the fuel air mixing can be enhanced. So that means because fuel air resistance time is quite low, that means in order to enhance the fuel air mixing, we have to increase the combustion chamber length. So which is not a viable option. So in order to address that, so we can use an obstruction like a strut here. So basically, strut is the leading edge of the strut is located at around 30 from the inlet channel. So its length is 80 and its thickness is around 6 here. So this is a typical strut which is widely researched on the DLR combustor, German Research Center. So again, in the strut injection, there are different cases: single strut, multi-strut, strut in cavity, and strut combined with wall injection and ramp in strut. So these are the different struts. So single strut and the different multi struts. So these are also various strut injection schemes. So actually, I'm focusing on blunting of the leading edge of the strut. So basically, when the strut is located in the combustion chamber, it is basically surrounded by high enthalpy gases. So it obviously leads towards some kind of thermal load. So thermal load on the strut is high because it is surrounded by high enthalpy incoming flow. So in order to overcome that, in order to reduce thermal load on the strut, blunting of the leading edge is one viable option. So which will basically reduce the thermal load, and it can be utilized for increasing the what is called as flame stabilization and to reduce the ignition delay. So because the strut, the blunting can extract more heat from the leading edge. So these are the blunting of leading edge. So we can see here the leading edge. Okay, the blunt can be. We can see that a cut of 10 see on the leading edge. So here it is 10 Another case it is 20 So we can see that. So that is this is a sharp edge strut, whereas this one is blunted blunted strut. So we can see here this here this width is 1.5 it is 3 here. So that is 10 is cut in case of first case, other case it is 20 cut. So that we can see here the sharp edges are formed here with this blunting. So the advantage with this is it can take more heat, so that thermal load on the strut can be reduced. So actually, I'm working on this H2 fuel scramjet engine to evaluate mixing efficiency, total pressure loss, and combustion efficiency at different Mach numbers. So I'm using wedge as well as diamond struts. These are most widely researched struts in case of strut injection and scramjet combustor. So I'm using this wedge and diamond struts, and they're blunting their leading edge. So we can see here this is a blunted wedge and this is blunted diamond strut. So this is actually wedge strut and this is diamond strut. So whereas this one is a blunted wedge and this is blunted diamond. And with this, I'm working on to evaluate static pressure, static temperature, density, and turbulence kinetic energy, and Mach number inside the combustion chamber by varying air Mach number from 2 to 3. So 2 Mach number 2, 2.5, and 3 are different Mach numbers, and hydrogen being injected at 1 Mach number. So I'm varying the hydrogen. I'm varying the Mach number of air from 2 to 3, keeping hydrogen injection at 1 Mach number. So I'm studying both this blunted wedge as well as blunted diamond, and another different aspect ratios as well to evaluate mixing efficiency and total pressure loss and combustion efficiency in case of scramjet combustion. So these are the inlet conditions for air as well as hydrogen. So air Mach number is varied from 2 to 3, whereas hydrogen Mach number is 1. So hydrogen is injected at Mach number 1. And the temperature of the air is 340, whereas hydrogen is at 250 Kelvin. And mass fractions of O2 in air, and this is mass fraction of nitrogen air. So there are certain challenges. Of course, the results I have recently communicated the mixing efficiency and total pressure loss efficiency, so that I cannot present now. So they are under review. So now let us discuss challenges associated with widespread adoption of hydrogen energy. So mainly to make hydrogen combustion a reality, there are certain drawbacks like there's hydrogen infrastructure and production cost of hydrogen, and due to low volumetric density of hydrogen, it requires large storage tanks, and safety concerns related to the hydrogen storage as well, and the development of infrastructure, safety issues, all these things will basically these are the hurdles for and also integrating the hydrogen integrating into carbon markets. So that is carbon what is called carbon capture and storage. So integration of this hydrogen production into carbon markets is also another hurdle. And also there are other obstacles like lack of differentiation. One is actually there is no established standards to distinguish low carbon hydrogen from fossil fuel based hydrogen. So there are no certain standards, and also there are no policies to. Actually, there are certain policies for hydrogen in road transport, particularly for fuel cell electric vehicles, and but for aircraft propulsion, there are no standards, policy standards for using hydrogen as a fuel. And also there are energy losses, which requires more renewable energy capacity. So these are some of the drawbacks associated with hydrogen as an aviation fuel. So these are the references I used. Thank you. Thank you very much.
Dear participants, do you have any queries or questions? You can post in the chat box. Sir, one question from the participant. In
Okay.
payload conditions, can we achieve fuel efficiency with sustainable fuels?
Yeah, actually, hydrogen is compared with kerosene, but in aviation fuel, sustainable fuels, I'm not sure actually. Hydrogen requires maybe and less fuel, as I discussed earlier, but sustainable fuels, I've not seen anything like that.
Sir, Basha sir, did you get the answer? Okay, thank you so much, sir. So anyone, you can ask your questions.
I don't understand the question actually. What parameter affect the efficiency? I don't understand the question. Please, can you please tell me the? No, actually, I don't understand what efficiency. Is it mixing efficiency or combustion efficiency or? Basically, this strut and the cavity they form some kind of shock wave, which will enhance the fuel air mixing, so that the efficient combustion is possible. So, because fuel air mixing is important for effective combustion, so by use of this strut as well as cavity injection strategies, we can enhance. Yeah, the combustion efficiency is basically some kind of, we are using this strut as well as cavities to enhance mainly fuel air mixing process. Okay, so these strut as well as cavities will generate some kind of shock waves which will enhance turbulence, so that fuel air mixing is possible. So combustion efficiency is dependent on fuel air mixing as well. So shock interaction that is caused by these obstructions, maybe due to the struts or cavity injection. So cavity creates some kind of turbulence and shock waves. So mixing is effective. So that means within the short combustion chamber, we can enhance the mixing effectively without increasing the combustion length. So we can use different aspect ratios for cavities or whatever it is. So we can enhance, we can change the aspect ratio of the cavities, or we can use bottom wall mounted or top mounted cavities. So that means by varying different parameters, we can study how effectively the cavity will enhance the mixing process.
Thank you so much, sir.
Okay, thank you.
So any questions from the participants? You can raise your hands. We can unmute you. I hope there are no questions. So thank you so much, sir, for your valuable presentation. We are delighted to have you as our resource person. Thank you so much, sir.
Thank you for inviting me, and thank you one and all.
Thank you, sir.
Now I'd like to introduce our second research person. Her name is Miss M.V. Chary. Good morning, sir. I would like to honor and introduce estimated guest, our Dr. Mr. M.V. Chary, a seasoned professional with an impressive 38 years of experience spanning diverse fields such as iron ore, steel, cement, power, waste to energy sectors, and academics. Currently, he served as the president of Jindal Urban Waste Management Limited, where he plays a pivotal role in driving innovative waste to energy solutions. Mr. Chary expertise include an extensive 22 years in project management, 12 years in maintenance and operation, and significant contribution to fabrication and academics. His accomplishments include the successful execution of over 100 green fields and brownfield projects, ranging from waste to energy plants to iron ore beneficial plants and DI pipe manufacturing units in India and abroad. As a visionary leader in waste management, Mr. Chary has been instrumental in commissioning key waste to energy projects in major cities like Delhi, Ahmedabad, Guntur, and Visakhapatnam, contributing to sustainable urban development. His dedication to research has led him to collaborate with international experts, including organizations in China, Japan, Sri Lanka, and Vietnam, to explore advanced technologies in solid waste management and energy efficiency. Mr. Chary contributions to academic are equally commendable. He has delivered impactful lectures on solid waste management at prestigious institutions including IITs and NITs and international universities like University of Geneva, and he also served as an advisor to several deemed universities in Andhra Pradesh and Telangana, shaping circular and faculty development programs. In recognition of exceptional work, Mr. Chary has received numerous accolades, including excellence certificates for project execution and the ICON as WMC Excellence Award 2023 for his best paper presentation, award for his pioneering efforts in solid waste management, including honors for the government of Andhra Pradesh. Beyond his technical achievements, Mr. Chary has traveled to over 20 countries for technical discussion, project collaboration, and knowledge sharing, endeavors reflecting his global impact in the engineering domain. We are truly privileged to have a leader of his caliber with us today. His vast experience, visionary thinking, and commitment to sustainability are an inspiration to us all. Ladies and gentlemen, please join me in welcome Mr. M.V. Chary to the stage. Let us look forward to gaining invaluable insight for his expertise and experience. Now, sir, I would like to handle you the stage. Thank you, sir.
Hello.
Yes,
Am
sir,
I
your
audible?
voice. Audible, sir. Audible, sir.
Okay. I am in a travel and I have a time constraint. Your program you have given is 7:30 to 9:30, something like that. Okay.
Yes, sir.
Kindly excuse me. I can participate for 30 to 45 minutes with you people. Okay. Now, who are all present in this VC and who are all physically witnessing my lecture? Can you please tell me?
My listeners to present here and
Can you please speak loudly? Hello? 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 Hello?
Sir, you are audible, sir.
Yes. You just, when I say you please respond. Okay. Now, the topic given to me is operations and maintenance. Okay. So, I'm not giving any presentations or anything. Okay. I'm just speaking extemporally regarding the operations and maintenance. While construction stage itself, we have to collect the total data of the different equipments. And first, the concept is the layout. Based on the layout, the equipment erection and everything to be planned. Based on the equipment, area-wise, the process flow to be defined. So the operations and maintenance, the first aspect is we have to create a process flow. Based on the process flow layout to be formed, accordingly the execution plan, and after that each and every equipment data. Here there are two kinds of equipments. One equipment will be totally supplied by the original equipment manufacturer, and after that in the site surroundings some erection will take place. So this and that data you have to totally cover in such a manner that the total to be documented. Particularly for operations, we have to study what is the raw materials, and based on that raw materials, the analysis and everything to be done, and specific consumptions also to be noted. Suppose there is a system. In the system, what is the input, and in the system, what is the output? For example, many of your college students and even your faculty visited our plant. In our plant, the system is compiled of boiler, flue gas system, turbine, air-cooled condenser with power generation. Here, the input is MSW, municipal solid waste. Okay, per hour, how much we are putting inside and what will be the residue generation. Suppose to make 1 megawatt in our plant, we need 2.5 tons to 3.2 tons of MSW based on the calorific value also. If the calorific value is high, the raw material required quantity will be less. If calorific value is less, the raw material quality is high. Accordingly, the residues also will be generated. So here in our plant, if I put 1 ton of MSW, okay, the power generation will be 0.3 units, number one, or 0.3 megawatt, okay, which is nothing but near about 300 units, 0.3 megawatt you take it, and the bottom ash generation, which is generating at the boiler bottom, it is 25% of MSW. So if I put 1 ton, near about 250 kgs bottom ash will generate, and the fly ash, which passes through flue, it is around about 2 to 3%, that is 2 to 3 kgs. And before that, the leachate is also generating. That is per ton, the leachate generation, it is around about 7%, 70 liters leachate it is generating. So this is the input. And what is the output? My output, it is power generation. So if you take the efficiency of the plant, on generation basis, the efficiency of the plant is 25%, means 25%, that is output by input, and on export basis, it is near about 21%. So this is the efficiency of the plant. Normally, what is the calorific value of MSW we are feeding? Our system in the plant can take gross calorific value on lower side is 1000 kilocalorie per kg. On higher side, it is 2000 kilocalorie per kg. And throughput, it is calculated at 1500 kilocalorie per kg. For example, whatever the plant you have visited, our boiler capacity, it is around about 600 tons per day. How they calculated 600 tons per day? At the calorific value of 1500 kilocalorie per kg. At this juncture, okay, to generate 1 megawatt, we need 2.5 tons of garbage. If it is less than 1500 kilocalorie, we need 3.5 tons of garbage. If it is higher calorific value, like something like 1600, 1800, we need only 2.2 tons of garbage. This is basically operational, this one. And not only that, the operation team should have the maintenance knowledge. Maintenance knowledge means electrical, instrumentation, automation, mechanical knowledge. And again, the maintenance team also should have operational knowledge. For example, a person who is operating the car, if he knows the minimum mechanism of how the car functions and small problems how to attend, then for him it is very easy to know how to operate the vehicle. For example, if one driver, if he operates the vehicle wear and tear, it is totally very less. The other driver, he also having same proficiency, but the vehicle wear and tear will be high. So similarly, if an operation person knows the equipment and all these things, how the equipment will be operated, accordingly, he can operate the equipment better. I had been to Japan, where this maintenance concept is totally removed. The operator who is operating the equipment, he only do the maintenance. Some multinational companies like Atlas Copco and this LG company, whenever any technician comes to us, the technician, he can handle mechanical, electrical, instrumentation, automation. So there is no separate person coming and visiting to this. So, and another most important thing, we have to focus 100% on the specific consumptions. For example, in our power plant, what is the specific water consumption? What is the specific steam consumption? What is the chemicals we are consuming? All this data we have to generate and we have to register. And we have to take, for example, if the plant is in operation for 38 months, something like that, then in such cases, out of these 38 months, what is the maximum production you have generated? Or what is the minimum and what is the average? And when maximum generated, what is the consumption? When minimum is generated, what is the consumption? All these things we have to record. This is called management information systems. And the total plant availability is depends upon how smoothly you are maintaining the equipment. For example, if you take a blower or fan, the fan we have run by some bearings and everything. How you are lubricating and what quantity of lubrication system we are using. What is the raw material as per the lubrication we are using, and what is the equipment manufacturer specification and how to operate the plant. For this purpose, we have defined this maintenance into preventive maintenance, predictive maintenance, breakdown maintenance. Preventive maintenance is that when the plant is running, we always have one standby, one running. So where there is no, in some equipment we can even do the maintenance in the operation time also. Sometimes what happens, for example, a turbine run for some 20,000 hours of operation. Then as per OEM requirement, we have to do the overhaul. For that purpose, what they will do, they stop the total equipment and they will open. It is just like that. Somebody is having car for 5,000 kilometers, one type of maintenance, from 10,000 kilometers, one type of maintenance. We have to follow exactly the OEM recommendations. Similarly, when the plant comes into the picture, what will happen? There are n number of equipments, and we have to assimilate all the equipments data and everything. Accordingly, we have to design the preventive, predictive, and breakdown maintenance. Sometimes what happens, all of a sudden, the equipment will be under breakdown. So when you want to attend this particular breakdown maintenance, when you want to attend that breakdown maintenance, then the safest thing is we need to have the spares. That is most important. These spares also as classified as emergency spares, normal spares, regular spares. So for any plant, for successful operation, we need to have store in position. The exact definition of store is every all items in its every item in the place, and a store is a place for everything and everything in its place. That is the definition of store. Okay. This is so store is another important aspect to support. This store is even it is there for the hospitals, even it is there for the college. If you take college, you have a stationery store. If you take a canteen, you have a food grain store. That is most important, something like that. So coming again to the plant maintenance operations, we have to see what are the regular consumables, what is the long-term consumables. For example, bearing is there. Its life is some 3000 hours, something like that. So after 3000 hours, what to do? You have to do the change of the bearing. Then this is called predictive maintenance. So if you don't do the predictive maintenance, suppose 3000 hours it is passed, still you are thinking that bearing is good. Then what happens? All of a sudden the bearing will be given away. During that time, we have to attend the breakdown maintenance. And another most important things for this plant operations, particularly in the main tools and tackles is the most important aspect. So that is most important. If you have proper tools and tackles, then the maintenance will be very easy. And another aspect is the SOPs. That is also another aspect. For example, all of a sudden some breakdown has happened. How to attend this breakdown? For this purpose, what we have to do, if a plant is in 38 months operation or 39 months operation, we have to generate a equipment history. What is that equipment history? This equipment has given failed in this particular aspect. Then how to attend? That is, we have to register in this one. And in this equipment, this bearing has given this much life. Based on that, we have to think that what happens when the bearing achieves so much of life. Then voluntarily what we have to do? We have to plan well in advance, because every plant will run for continuously 1 month or 2 months or 3 months. After 3 months, you have to have a planned shutdown. That is also called opportunity shutdown. Means we are predicting something and we are attending each and every equipment in the plant, okay, such that the breakdowns will not occur. So this maintenance aspect, again, it is divided into preventive, predictive, and breakdown maintenance. Once this is attended thoroughly, then your plant availability for that is called equipment availability for continuous operation. It is very good. For example, if I take in our case, in a month, some months we are running continuously. Some month, 1 or 2 days, we are stopping the plant. Sometimes in this particular waste energy plants, what happens? If you want to see the internals of boiler, some puncture, something like that, we have to stop the plant. And at the time of stopping the plant, there is a procedure how to stop the plant. And after that, we need minimum 2 days time to enter inside the furnace. So the total maintenance, it takes 2 to 3 days time. So such kind of things happen. The plant particular equipment needs to stop. Along with this, whatever the related equipments also, we have to check thoroughly. So that once the boiler is ready, after that, when you don't check the related equipment, again, if that related equipment is a problem, then again we need to stop the plant. This is called planning of maintenance. So under the planning of maintenance only, just now I explained preventive, predictive, and breakdown maintenance. Next, operational efficiencies, operational optimization, and everything. For example, in my boiler, The pressure parameters is 40 bar, temperature is 400 degrees centigrade, and the steam generation near about 50 tons, something like that. It totally depends, and we are generating power at some 15 megawatt, 16 megawatt. So the plant load factor, that is another important aspect. The definition of plant load factor, if you take our plant into consideration, our installed power is 15 megawatt. That is constant. But generation, I can generate 10 megawatt, 12 megawatt, 15 megawatt, something like that. If I generate 15 megawatt, my plant load factor is 100%. If I generate, for example, 16 megawatt, it is 104%. If I generate near about 10 megawatt, 10 by 15, it is around about 80, 85%, something like that. So based on that, the plant operations also can be decided. And another important thing is we have to see maximum to the extent possible. Plant has to run continuous operation at the desired parameters, because for any plant, the fluctuations is very dangerous. Today you are generating 10 megawatt, tomorrow you are generating 15 megawatt. These fluctuations will definitely damage the equipment. That is most important. If you want to run the equipment in low capacity. If you want to run at higher capacity, but don't run in the fluctuations. That is most important. So another important aspect is the economy. That is at what cost we are generating the power. That is most important. If I run my plant at 95% PLF, my unit generation cost, it is around about 5 rupee 50 paisa. And I am going to get for unit export, it is around about 6 rupee 30 paisa, something like that. So the difference is near about for every unit, it is 80%. If I run my plant at 90% PLF, my unit generation cost, it is going up to 5 rupee 80%. My profitable margin, it is coming down. So always run the plant at highest efficiency. Okay, this is most important. Hey, right side. Left. You understand? I hope you are understanding this one. So finally, I'm coming to a conclusion that for any plant operations, we should have thorough knowledge of each and every equipment and equipment data, equipment operation history. These are the most important. For operation maintenance aspect, we have to have again the data and OEM recommendations. What is the kind of lubricants, everything to do. So this compiles overall plant operations and maintenance. So I'm taking a break. If anybody having any questions, you please ask me. Hello? 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 Hello?
Dear participants,
Uh,
do you have any
Anybody?
questions? If you have any questions, you can ask.
Hello? Hello?
Dear participants,
Hello? Okay. If there is any no questions, I am concluding like this. For effective operations, the management information systems is most important, where it defines the specific consumptions, equipment operational data. This is one aspect. And another important aspect as per the maintenance concern, the effective, predictive, preventive, breakdown maintenance and its procedures, it is most important. For all these things, at the plant construction stage only, we need to have each and every aspect. And another aspect for the plant operations most important is training. That is most important. We have to call the expert people to give the lecture about different equipments. For example, in our plant, the hydraulic system is there. Very limited people, they know only hydraulics. Then we invited one expert who carried out the training, and after that he took all the staff and to the equipment. He has explained in detail about the each and item of the equipment, each and every item of the equipment. Okay, this is the thing. If anybody asks any questions, I will answer. Otherwise, I want to close the session and I want to go because I'm very sorry and it is unexpected. I'm going to have a travel immediately, so I'm rushing to the airport. Please. Hello. Hello.
Sir, one question from the participant.
Please.
Frequently, ESP came to break down 600 megawatt power plant shut down 6 to 9 hours. How can we predict the failures, sir? So one of the participant is asking this question.
Okay. ESP, particularly, we have to see the maintenance aspect, timely maintenance. That is most important. Another important aspect is the current loads, how it is taking. That is another important aspect. Next is whatever the particle size it is coming. That is another important aspect. And in the chimney, how the flue gas emissions, that is also important aspect. 99% of ESP fails once the equipment you have taken a standard equipment, it is purely operational mistakes. And maintenance, in time maintenance, if they are not attending, then it is a problem. Because there is nothing to do with the operation. It is purely in time sequential maintenance that is most important for ESP.
Thank you, sir. And one more question from the participant. So how the waste which can be generated after combustion will be utilized?
You see here, I told just now the residues. 25% of waste generated, combusted will be the bottom ash, and 2 to 3% the waste combusted will be fly ash, and 7% whatever moisture present of MSW will be the leachate. Now this bottom ash and fly ash,
And
the other one is bricks made of ash, that is power plant ash and everything. I want to save the gravel because to form 1 gram of gravel in nature, it takes 950 years. So we have to use this waste material and preserve the natural resources. And whatever the leachate it is coming out, the BOD, the limit it is 35 milligram per liter. In the leachate it is 20,000. And COD, the limit is 250 milligram per liter. The COD of the leachate it is 80,000, something like that. The TDS, good it is allowed is 500, it is around about 2000. In our plant, we are treating the leachate in a process called aerobic, anaerobic, dual multi activated carbon filter, next ultrafiltration RO systems. So we are taking the product water, which is just like drinking water, where BOD it is 30, COD it is around about 220, and TDS it is around about 500. This product water we are again using for the steam generation. Reject water we are using for the ash quenching. Okay. Hello. Hello.
Thank you, sir.
Okay. Anybody? If nobody, I want to leave the VC.
Dear participant, do you have any questions? You can ask. Sir will answer.
If the participants interested also, they can come and visit the plant. It is a unique plant. Daily we are taking 1200 tons of garbage, and per hour we are generating 15 megawatt power.
Thank you so much, sir, for inviting the participant to visit the plant.
Yeah. Okay. Can I leave, please?
Thank you so much, sir, for your valuable information. Even though if we are in a busy schedule in travel, just you have contributed so much of knowledge for our participants. And from on behalf of our management, we are very thankful to you for spending some time with us to contribute our knowledge. Thank you so much, sir.
In one of the day, if possible to me, I will come to your university to interact with the students,
Thank you
where I
so
want to show that solid waste management PowerPoint presentation. And after that, our plant video, all these things we can interact with the people. Okay.
sure, sir. Thank you so much.
Right. Thank you. Thank you.
Thank you, sir.
Dear participants, due to some busy schedule of the resource person, so we have to stop our session up to this point. So we'll get a Google form link so that you can fill the details for attendance purpose. So tomorrow we'll have the session exactly at 6 p.m. with other two resource persons. So try to fill the attendance sheet. So just find the attendance sheet or Google form in the chat box and as well as in the WhatsApp group. Thank you so much.